Hi everybody, Greyfeast here. Today I'm going to be talking a little bit about the proof that there are an infinitely many number of primes. Prime numbers are important for a couple of reasons. The first is that they're used in a lot of higher mathematics, particularly in number theory and analysis. They're also useful in encryption. For example, the banks use very large prime numbers in order to transmit secure data, and the military uses it for that reason as well. So I'm going to go ahead and get started. The axiom that we're going to be building off of is that every integer is the product of prime numbers. And that product is called the prime factorization. Now that can be proved pretty simply. I'm not going to go through it here, but it's pretty easy to convince yourself that every integer can be decomposed into the product of several prime numbers. So in order to prove that there are infinitely many primes, we're actually going to assume the opposite. Suppose that there is only a finite number of primes. For example, let's say that there are only 5 numbers. This is the proof by contradiction, which is very common in mathematics. So we'll go ahead and say that the prime numbers are 2, 3, 5, 7, and 11. Now, with those 5 numbers, we're going to take their product. The product of 2, 3, 5, 7, and 11 is 2,310. So now we ask the question, what is the prime factorization of this number plus 1? So for example, in this case, 2,311. Well, 2,311 happens to be prime, but just to show that none of the prime numbers that were used to construct this number are divisible, you can see here that if we divide 2,311 by 2, 3, 5, 7, or 11, we don't get any integers. They're not exact divisors. So we can conclude that 2311 is not divisible by any prime of the 5 that we've allowed. This is because each prime divides the product, but not the 1 that was added to it. So because we've reached a contradiction with our first statement, which is that all integers are divisible by primes, our initial assumption that there are only 5 primes has to be incorrect. This proof can be repeated for any finite number of primes and can be generalized. So here you can see if all primes are contained within the finite set P1, P2 to Pn for some n in the natural numbers, then Pj, where Pj is a member of the finite set of primes, does not divide 1 plus the product of all primes. Again, for the same reason, the Pj is contained within the product, which is the right-hand term that looks like a pi symbol, but Pj does not divide the 1. Therefore, we can conclude that there must be an infinite number of primes. So hopefully that was clear to you. Hopefully you've enjoyed learning about this relatively beautiful proof. I think it's a beautiful proof anyway. So hope you enjoyed and look out for more of my videos. Thank you.